In this recording, we will talk about collisions. Now, one of the areas where conservation of momentum is quite applicable and quite useful is in the study of systems where we have objects that collide. It is quite useful because in worrying about initial and final momentum only, we don't have to worry about the interaction that happened between the initial and the final momentum. That makes the study quite simpler. And also the fact that when we have a system of particles, we don't have to worry about the interaction between these particles. That makes the job easier as well. Now, for example, let's take this case here, a collision between two billiard balls, this one here and this one here coming in at high speed. Now, what this tells us is the momentum before the collision is the same as the momentum after the collision. In this particular case, for example, the momentum before the collision would be the momentum of the red ball, it looks red, the one moving, plus the momentum of the 8 ball. So that's the momentum before of my system. And let me put the arrows for direction. Now, if I choose this as the positive direction, this one is going to be positive, and this one is 0, since we started with no momentum, it's not moving. What this tells me is what's going to happen after the collision. My momentum, my overall momentum, is going to be the same as the momentum that this initial red one has. For example, in the case of billiard, most of us know if we hit the ball head-on, then what we are going to get, this ball is going to start moving with the same speed that this one had upon impact, and this one is going to stop. Okay? Now, that's conservation momentum collisions. The momentum before the collision is equal to the momentum of the system after the collision. Okay, a few reminders. Momentum is conserved even when energy is not. And we'll talk about it later on, but explosions are also considered collisions. It's a reverse collision of sorts. Okay, let's talk of several examples. Now, in the particular cases that are illustrated by the pictures here, like here we have this guy and this guy coming in towards each other and colliding. So this is their initial masses and velocities moving towards each other, and the final momentum. Now, if they are going to bounce off each other, then that would be my final momentum, the momentum of the yellow mass plus the momentum of the blue mass, but we have to take into account directions. If they stop, then the final momentum is 0. Now, let's just focus on this for a second. If I take this as my positive direction, in this particular case, the momentum of mass 2 initially is negative. The momentum of mass 1 is positive. Here, the momentum of mass 1 is negative after the collision. The momentum of mass 2 is positive after the collision. But the sum of these two should be the same as the sum of these two. Collisions happen between, I guess here, I think that looks like baseball players. Now, it also happens between cars. So the momentum of this car plus the momentum of this car before the collision is equal to their momentum after the collision. Now, if they had equal momenta initially, then if they have equal momenta, they are moving in the opposite direction, equal in magnitude, then their overall momentum is 0. So if they hit and stop, that means their overall momentum is going to remain 0, since it starts at 0 to begin with. Collisions are quite important. Actually, a lot of us believe that the dinosaurs have ceased to exist on Earth because of a collision of the Earth with a comet. We have seen one collision of another planet, Jupiter, in 1994 with Thomas Shoemaker-Levy in July 16, 1994. Now let's look at some examples. What I'm going to do here, I have a few videos that I'm going to show and describe them while we see them. Okay, now the collision. I'll play it again. Notice here, these two cars, they had the same momentum along this direction. So what happened is the overall momentum along that direction remained zero. Okay, so we started with both of them moving with the same momentum in opposite direction. Now, so that adds up to zero. So my final momentum along that direction should be zero, and that's why we don't see a net motion along this direction. Along the perpendicular direction, there was no momentum to begin with, and there should be no momentum at the end. So if one of them is going to move in one direction, the other will move the opposite direction. So the red one is moving up, the green one is moving down. Conservation momentum along the vertical as well. So in this particular case, we started with a horizontal momentum of zero because they had equal momenta in opposite directions. And we ended up with a zero momentum along the horizontal because they both stopped from moving along the horizontal. And then along the vertical, we started up with zero momentum along the vertical because neither one of them was moving vertically. And then both of them started moving with opposite momenta along the vertical, resulting in a zero momentum along the vertical again. So we have conservation momentum along both directions. Of course, here what we need to remember, what I'm calling vertical is not really a vertical. It's one direction and then the perpendicular direction. It's vertical in the case of the screen here. Okay, let's see another case. Let's see here. We are going to have a collision here between a massive object and a less massive object. This is a street camera that took the picture. See there. Oops. Now the car, during the time of the collision, so actually was essentially stopping, was not moving anymore. Of course, we notice what happened to the gentleman. Unfortunately, who knows what happened to him? Okay, he kept on moving. An object in motion will keep on moving in the same direction unless acted upon by an external force. So he was moving in the forward direction. There was nothing to stop him, so he kept on moving. The momentum of the car is larger than the momentum, or I'm not sure if it is larger. It has a bigger mass, but it's in the opposite direction than the momentum of the bike. As a result, so actually it looks like they have probably about equal momenta in that head-on collision. That's why we don't see the bike moving back that much or the car moving back. So the overall momentum still remains zero. Okay, now let's see another case. I'm just doing this for the fun of it. A crash of two locomotives. Same momentum along the X for both of them, but opposite directions. So when they collide, they just stop there. Okay. Now collisions don't happen only head-on. Now in this particular case, so we have a car moving, and then the other car is going to come hit it, and then you notice there for a little bit I stopped the movie, they start moving together. Now here, what happens is my initial momentum is going to be the momentum of the middle car plus momentum of the rear car. In this case, both of them are in the same direction. Now, the momentum of the rear car is probably larger than momentum of the middle car, but regardless, the overall momentum is both of their momentum. Now when they move together, so it's going to be the momentum of both cars, rear and middle. Now that momentum, in this case, we can very easily account for it, but if objects are going to stick together and move as one object, they are going to be mass of the rear car plus mass of the middle car times their combined velocity. And that should be the same as their individual momentum before the collision. Okay, now in this case we take the situation further. What's going to happen here? Now as the three of them move, the momentum of all three of them is the same as their initial momentum before the collision. Okay, let's see this other one. This is very interesting. Okay, you see that? Okay, so now in this case you notice if I start with something with a much larger mass, the others are not going to stop it much. Okay. Notice here another one. This is a police chase, but you notice even though he flipped, the guys kept on moving in the forward direction. Okay? So momentum is still conserved. Momentum is along the forward direction, so it's going to stay in the forward direction. What about sideways collisions? Okay, let's see an example here. Okay, we have that car, and look what happened. So what we have here, initially we have momentum along this direction, and momentum along this direction. So what should happen? Both of these momenta should be preserved. So that's why we see what happens. This one moves forward, and it moves this way. So overall we have conservation momentum. Of course, you see, once the cars brake and everything else is going to happen after the collision, that's a different story. But during the collision, the momentum along this direction and the momentum along this direction both were conserved. Okay, let's see it in a lab setting where it's easier to see. These are actual cars, by the way. Okay, notice here when you hit that car, we still have this motion here. Is actually both a motion like this and a motion like this. It's a motion like this and a motion like this. So we still have this momentum that remains unchanged and this momentum that remains unchanged. Now, we talked about momentum, and momentum is conserved in all directions. It can be conserved in 3 dimensions. Here, this is a historic picture of an aerial collision. In that particular case, you worry about momentum conserved height-wise and x and y. In all 3 directions, it is conserved in all 3 directions. Here also, we can talk about 2-dimension collisions and these soccer players. Both cases, we have conservation momentum as these players collide.